Well, we have somebody that still hasn't taken them yet, so until that last of the makeups get done, I'm going to hold on to them. But the grades have been posted. Okay, so we're going to start with a bunch of vocab and notation here. The first thing we're going to do is define a vector. So a vector is a new type of quantity. So a vector is defined as a pair of real numbers which represent both a magnitude and a direction. So this is the third different type of quantity we've probably talked about in our mathematics education. So we've talked about numbers, spent a lot of time talking about numbers. Last year in your algebra course, you talked some about matrices, which is a decidedly different type of quantity than a number. And now we're going to be introducing you to the third type, which is called a vector. A vector is a decidedly different from a real number. Depending on how you want to define things, it can be similar to like a matrix, but you wouldn't really see that until you took like a linear algebra course as a college student. But there is some nice overlap between matrices and vectors, but we're not going to deal with that here. Okay, so we have a bunch of different representations for vectors. The first one that we're probably most familiar with is as a magnitude and direction. And we've seen this description already in the first semester. We did some vector story problems in first semester. So for example, we talked about maybe a 20 mile per hour wind blows at a bearing of 120 degrees. So the speed here is our magnitude, and our bearing is going to represent our direction. So this is a common description for a vector. It's a nice description in that it has kind of some real world corollary to it, where like saying the magnitude is such and the direction is such kind of has some real world meaning to it. So this is often the way that story problem questions would be phrased, and answers to story problems would be given as be like in this kind of a form. The next one would be component form. So the way we denote a component form for a vector is we use these wedge brackets. So when we denote a vector quantity, typically to differentiate that from just a normal variable, we'll put the little vector hat on it. In the text, we're going to use boldface letters to represent our vector quantities rather than our variable. So kind of be cautious about that if you're reading the typed out notes. Or looking at a textbook, they'll often do that. As opposed to putting the hat in, it's a little bit easier to typeset that when you're writing a book. It's like an arrow like that is the symbol that I'm using there. So the thing to remember about component form is when we write the vector in component form, that vector AB, that tells us that the beginning of our vector happens at the origin and the end of our vector happens at the point AB. So we have to be really careful with our symbols here, right? The parenthesis AB is a point. The wedged bracket AB is a vector in component form. So we have to make sure that we're being consistent and careful with our notations here, because if we just say AB, it's not clear whether that's a point or a vector, right? So we have to be careful about that because they mean different things. That's a V with a line above it. So there's a geometric interpretation for a vector. So maybe this is my vector V here. So if I draw in like an imaginary XY axis, the direction for my vector would just be my standard form angle. And the magnitude for my vector is just the length of the line. Okay? So again, a picture can represent that same information because it gives you a direction and it gives you a magnitude, right? And the fourth representation we'll talk about here in the first section is as a pair of points. So say vector A is the point x1, y1, and B is the point x2, y2. Then the vector AB is the vector with initial point A and terminal point B. So when we say initial point, that's like the tail of our arrow, and terminal, that's like the head of our arrow. In this form, the order that we write our letters is very important. So the initial point needs to be the first one, and the terminal point needs to be the second one. Very similar to the same notation that you used when describing a ray in your geometry course. Remember when you named rays, the order of the letters mattered, right? Or the direction you drew the arrow on top of the letters mattered. Some people like to do it that way. I don't like to change the direction of the arrow. I'd change my letters. And then there's a fifth representation that we'll talk about a little bit in section 8.2. But these are the four beginning ones that you'd see. And what we're really interested in doing here initially is being comfortable moving back and forth between these different representations. Sam, did you have a question? Okay. So the first one is going to be going from pair of points to component form. So if A is the vector x1, y1, A is the point x1, y1, and B is the point x2, y2. If I want to write the vector AB in component form, I can calculate that by doing x2 minus x1, comma, y2 minus y1. This is commonly referred to as the head minus tail rule, because we take the, thank you, Miguel, this is for you, because we're taking the head of the vector and subtracting from it the tail of the vector. Let's look geometrically at what this is doing and why this works. Because without an explanation, this is just a formula, and that makes it hard to remember, right? If we understand what's going on and the formula makes sense, much easier to remember. Okay. So here's my xy axis. Here's my vector AB, right? To put it into component form, I need it to go down here. Everybody okay with that? This is just a geometric transformation that I'm doing. Which type of transformation would I do to move that vector to a new location? Do you remember which type of transformation is going to pick up and move an object to a new location? Shift or translation, right? So if I was going to move this vector, how much would I have to move it to the left? x1, right? And how much would I have to move it down? y1. Everybody agree with that? So if I translate A to the left x1 and down y1, its new location would be at 0, 0. If I do the same thing to point B, its new location would be at x2 minus y, or x1 and y2 minus y1. Hence the component form formula, right? The initial point is now the origin. That's part of the definition of component form. And its terminal point is now x2 minus x1, y2 minus y1. Is everybody okay with that idea? Okay? So if the magnitude is equal to the length of the vector, if I'm given 2 points, A is x1, y1, and B is x2, y2, the magnitude of AB then is just going to be the distance between these 2 points, right? So going back to geometry, I could use the distance formula. If I'm in a 2-point notation, I can just use the distance formula to calculate the magnitude. If the magnitude is just the length of the vector, that's just the distance formula. I mean, you should know that. If we have a vector in component form, what does this simplify down to? Yeah, basically, or you can think of it as my terminal point is AB. My initial point is 0, 0. A minus 0 squared is A squared. B minus 0 squared is B squared. So either way, yes. Yep, it's doing the same thing. Everybody okay with that idea? Yes, of course. So let's look now at how we go from a component form to a magnitude and direction. Actually, we should probably do this. So I'm going to do it actually. That is my example. So here we're asking to convert from two-point form to component form to magnitude and direction. So I'll first convert to component form. So it's going to be x2 minus x1, y2 minus y1. Everybody okay there? Now that I am in component form, it's easy to calculate the magnitude. I can use just that formula that I've used before. As a quick aside, notice that the formula, or the notation for magnitude, we're using these vertical bars. This is the third different use we've seen for the vertical bars. So the first thing you've seen using vertical bars was absolute value. In your algebra course last year, you probably saw we used the vertical bars to represent the determinant of a matrix. And this is now the third different time we've abused this vertical bar notation to imply the magnitude of a vector. Now keep in mind, it should be clear from context which one of these three you're talking about, right? That there is no such thing as absolute value for vectors or matrices. There's no such thing as the determinant of a real number, the determinant of a vector. And there's no such thing as the magnitude for a real number or the magnitude for a matrix. So depending on which symbol those vertical bars are around, it should be clear what we're talking about, whether it be determinant, absolute value, or magnitude. But we do abuse the heck out of that notation and use it for a couple of different things. All right, we still need to determine the direction, though. So we already know how to do this. We've done this in first semester. What I'm going to do is I'm going to graph my vector here. So I plotted the point -8, -7. And my direction is going to be this standard position angle. So to calculate this standard position angle, I'm going to draw a reference triangle like I would have in first semester. And what I'm going to do is I'm going to calculate this little angle here, alpha, because I know that my direction is going to be 180 degrees plus that angle alpha there. Well, this triangle have side lengths of 8 and 7 because I went 8 to the left and then 7 down to graph that point. So I can do tan inverse of opposite over adjacent. And when I type that into my calculator, I get, 41.19 degrees. So my direction then is 229.19 degrees.
Sorry, what was alpha's value?
Right here?
Yeah.
41.19. You're asking the number. Okay. Right, and this looks very familiar. This is exactly a kind of problem that we did in first semester, right? Exactly the kind of thing that we would have done in first semester. So finding the direction from component form, all we're doing is plotting our point and finding out the standard position angle. Okay? Now what we want to do is look at how I take a magnitude and direction and put that into component form. Sometimes this process is also called resolving a vector. So let's say we want to find the component form for a vector v that has magnitude of 5 and direction of 224 degrees. Before we write the formula for this, let's just kind of imagine what it is that we're doing and justify where this formula is coming from. So if I draw a 224 degree angle, I'm going to be somewhere here, right? Everybody agree with that? I know the length for this angle then is 5, or the length of the side when I draw my right triangle is 5. So basically what I want is that I need the side lengths for that triangle to figure out my components for the component form. Okay. So that's just going to be the magnitude of v times cosine theta and the magnitude of v times sine theta. So in this case, I can do v equals 5 times cosine of 224, and then 5 times sine 224. And when I type this into my calculator, I get approximately negative 3.60, comma, negative 3.47. Notice here I didn't have to worry about the fact that these x and y's were located in the third quadrant and have to mess with the signs anywhere on doing that. Why didn't I have to worry about that? It's because I used the 224-degree angle as opposed to the size of that angle inside of my triangle. If I use the size of the angle inside my triangle, then I have to worry about making sure my signs are correct. If I use the standard position angle, the sine and cosine of a 224-degree angle are each going to be negative because they're each in the third quadrant already. So using the standard position angle there kind of saves me from having to worry about the signs of those things, which was often, depending on how that problem was phrased in first semester, was something we did have to worry about, right? Okay. So, next up, we're going to start talking about vector operations. So when we say vector operations, we mean things like add, subtract, multiply. Well, it turns out there's actually a couple different kinds of multiplications for vectors. But before we can get into any of those things, I need to define one very special vector. It's called the zero vector. Which we denote as the number 0 with the vector hat on top of it, because the zero vector is not the same thing as the number 0. What do you suppose the component form for the zero vector is going to be? Just take a guess. What would you hope? BA. Be more specific. How about 0, 0? I heard somebody say that. Denoted.
I can't read his brain. It's not my fault.
So, if the component form for this vector is 0, 0, what's its magnitude going to be? 0. And what's its direction then going to be? No.
We don't know. Infinity.
Questionable is the closest thing to the correct answer. The zero vector is the only vector that has no direction associated to it. If your vector is the points 0, 0, and 0, 0, what the heck would your standard position angle look like? There wouldn't be one, right? Because you can't draw something, there's no terminal side if its points are both the origin, right? You can't draw a standard position angle on that. So the zero vector is the only vector that contains no direction. Okay? For example, the vector 1, 0 would have a direction of 0. And that's okay. Different than no direction. All right. Next thing here is vector addition. So the way we add vectors is just add them component-wise. You just take the x components and add them, and the y components and add them. This is one of the reasons why component form is such an important way of representing vectors, is it makes these sorts of calculations very, very easy. If we were doing the same thing geometrically, so let's say here's my vector u, and this one is my vector v. If I wanted to add them together, what I would do is I would draw my vector u. Oops. And then I'm going to draw like an imaginary xy axis whose origin is at the terminal point of u. And then draw in my vector v. And then this vector from the origin to the end of vector v is my vector u plus v. So to figure out the magnitude and direction of that, you're talking about multiple applications of the laws of sines and cosines, and it becomes a pretty messy endeavor trying to do this geometrically. You do a component form, piece of cake. As an aside, when you talk about the sum of two vectors, this vector u plus v is also sometimes called the resultant. Mark. Sure. Okay. Next up is the first kind of vector multiplication we're going to see. It's called scalar multiplication. So we say that the scalar product of a scalar, and FYI, when I say scalar, do you guys know what I mean? A scalar is just a real number, like 7 or a half or 15 or the square root of 2 or pi. It's like a non-vector quantity, just a real number. And some vector, if I multiply a real number times a vector, well, what happens? I just multiply the real number to each of the components. So geometrically, what's going on here? This is my vector u. That would be like my vector 3u, where I've just stacked that same vector u on top of itself 3 times. So if we think about this, is scalar multiplication going to change the magnitude? Yes, right? How much longer than u is 3u? It's 3 times as long. Is it going to change the direction? No, right? Still the same direction. Okay. Is this far enough? So the next thing we'll talk about is the vector additive inverse. So let's go back to like elementary school here and talk about just additive inverses in general. So let's say we have the number 5. What's the additive inverse of 5? -5. Why is -5 the additive inverse? Well, when you add them together, you get 0. Okay? So let's say we have the component form vector 3, 5. What's the additive inverse of that vector going to be? -3, -5, right? That's the idea. Okay, so it's the same thing that you've seen before. How do you suppose we're going to denote that vector that's the additive inverse of u? What symbol do you think we're going to give it? What? -u. Right? Just like we did for -5. Why did we need to define scalar multiplication before we did this? Because -u is really the same thing as just -1 times u. Now, quick question. We saw that 3 times u changed only the magnitude and left the direction alone. What is -1 times u going to do? Is that going to change the magnitude? No. What is it going to do, though? It will change the direction, right? So if this is u, -u would be down here, right? How much is it changing the direction by? Very good. It's a 180-degree change in direction, right? Is everybody okay there? Okay. So we needed the scalar multiplication and this vector additive inverse to define what operation? Subtraction. Oh my goodness. Okay. So the difference of vector u and v is just going to be the subtraction of the vector's components, just like vector addition was. Vector u minus vector v is the x component of u minus the x component vector v. And then the y component of vector u minus the y component of vector v. Works exactly as we'd hope it would, right? So the next thing we'll define here is something called a unit vector. We say a vector u is a unit vector if and only if the magnitude of u is equal to 1. And guess what? You guys already know all of the unit vectors. Why? The unit circle, very good. Remember the unit circle from last semester. So if this is my vector v, what is the length of this vector? It's 1, right? Because it's a unit circle, the radius is 1. Everybody agree with that? And the point here is sine theta comma cosine theta. So every unit vector is of the form sine theta cosine theta. Or sorry, cosine theta sine theta, excuse me. That's pretty convenient. So the next thing we're going to talk about is we're going to develop a formula to find a unit vector in the same direction as a vector v. So let's think about what this is that we're trying to do. So here's my vector v. If I want it in the same direction, I just want u to be like that, right? Everybody okay with that idea? Visually, what it is we're trying to do. Has the direction changed? Has the magnitude changed?
Yes.
Do we know of an operation that leaves the magnitude the same, or the direction the same, but changes the magnitude? Scalar multiplication, right? We just saw this a few minutes ago. So I know that u is going to equal something times vector v, right? Everybody's okay with that much? We're not sure what that something is yet. We're going to fill that in a moment. But it's going to be some real number. So let's think about this as just a thought experiment. Let's say vector v has magnitude of 5. What would I have to multiply vector v by so that it would not be a unit vector? What?
You said it was 5, right?
Yep, 1/5. Because 5 times 1/5 is 1. Okay? So now let's be a little bit more general. 5 was the magnitude of vector v in this case, right? So what does this need to be here? 1 over the magnitude of v. So let's say, for example, I want to find the unit vector that's in the same direction as the vector 5, -6. So I know I'm going to use this formula, right? To be able to use that formula, I need to calculate the magnitude of V. How do I find the magnitude of V again? We have a formula for this. It's the square root of A squared plus the square root of B squared. So 25 plus 36 is 61. So filling things in, I have 1 over the square root of 61 times the vector 5, negative 6. Okay, how do I perform that scalar multiplication? I just multiply the scalar to each component. That's going to give me 5 over the square root of 61, and then negative 6 over the square root of 61. Everybody okay there? Do we like the form that answer's written in?
Yes.
No. Why not? The square root's in the denominator, right? How do we fix that? Yeah, multiply the top and bottom by the square root of 61. So we have that. Now, yes, Sam, of course. The calculation for that, not bad, right? Not terribly complicated, not a lot of steps. But what you did have to remember is how to do all those little things, right? You have to remember how to find magnitudes. You have to remember how you do scalar multiplication. You had to remember what a unit vector is. You know, like there's a lot of vocab and little things that you have to remember how to do, but the actual procedure there is not terribly complicated. It's just getting through the notation and the vocabulary to getting to what we care about, right? Now there's 2 unit vectors that are of particular importance to us. And because they are important, they're going to get special names. The first one is the vector I, which is the vector 1, 0. And the second one is the vector j, which is the vector 0, 1. These 2 vectors are important because they unlock a fifth representation of a vector called the linear combination form. So let's say we have some vector v that's represented as vector AB. So let's see how we go from component form to a linear combination form. So vector v is the vector AB. Well, that's got to be the same thing as just A0 plus 0b, right? By vector addition, we can just break the vector apart like that, right? Still equals the same thing. And A0 could be the same thing as A times 0, 1. Or I'm sorry, 1, 0. And 0b could be the same thing as B times 0, 1. And remember, 0, 1 is my vector I, and 0, 1 is my vector j. So this is my linear combination form here. It's written as the sum of these two unit vectors, or a scalar times the unit vectors. And we're going to stop here for today. So we've done enough now for you guys to work on 1 through 22. On these problems, when you're working on these, the thing I'd like you to pay special attention to is the notation and the vocabulary. That's the important part right now. Okay? Understanding what it is that we're being asked to do, what the symbols mean. That's the place where you want to focus your attention. If you understand those things well, doing the problems are not difficult, but you have to know like what it's asking you for to do, and then how to do those things. Okay?